Okay, we're continuing with Chapter 1 in the geometry textbook. In this video, we're going to go through Section 1.3, which is on early definitions and postulates. So as the title of this section suggests, we're just going to be presented with some definitions and postulates that we'll be using throughout the course. But what is a postulate? What exactly is a definition? But what does a postulate mean? All right, a mathematical system. Like algebra, the branch of mathematics called geometry is a mathematical system. The formal study of a mathematical system begins with undefined terms. Building on this foundation, we can then define additional terms. Once the terminology is sufficiently developed, certain properties or characteristics of the system become apparent. These properties are known as axioms or postulates of the system. More generally, such statements are called assumptions in that they are assumed to be true. Once we have developed a vocabulary and accepted certain postulates, many principles follow logically as we apply deductive methods. These statements can be proved and are called theorems. The following box summarizes the components of a mathematical system, sometimes called a logical system or deductive system. Okay, so what they're talking about here is that what you can think about is to build any subject in math, or just to build math in general, and really just science as well. Everything needs to be pretty bulletproof. You know, you really shouldn't have things that down the line, after they've been formally defined and built upon, be contradicting themselves. So you have to be very careful, very systematic about statements that you make, about how you define things, about what you state to be truth. Okay. Now, but what's interesting, though, is that contained within the four parts of a mathematical system, and really this is true of any kind of science system you're building, is this idea of an axiom or a postulate. And what that is, it's like they stated, it's statements that you assume them to be true in the sense that they don't require proof. We're going to see that, you know, like a theorem requires proof, but an axiom or a postulate doesn't. So how could you have these features that don't require being proven, that you're accepting as true, and still have a bulletproof mathematical system, or just a system in general? Well, you do this all the time in casual conversation with your friends and family and whoever. You know, it's like if you're discussing some of the funniest movies you've ever seen with your friend. That's the context of the conversation, and y'all are going over a set of 5 or 6 movies that both of you thought were hilarious. There's no doubt that both of you, in the context of the conversation, think that those movies are funny. It's just about which one is funnier than the other. But what you can think about, though, is that whenever you're making an argument about one of the movies, you don't have to prove that movie is funny to your friend if he or she already agrees that it's really funny. Y'all both have laughed hysterically at the movie countless times, right? I mean, technically, you might have to prove that, right? I mean, what does it mean for something to be funny? Is it actually funny? Is the movie actually funny? We don't know. Maybe we have to do some psychological analysis to see if it's actually funny. That's ridiculous. Both of you agree it's funny. That's established. We're not going to have to go through a proof to show why it's funny. We just know it is. Common sense, our intuition. We both laughed at it. We both thought it was the funniest thing we've ever seen. You know, you can look at definitions as postulates. You don't need to prove a definition to somebody. If that's the definition, then that's the definition. We're both agreeing that that's true. There's no need to prove it because it's a definition. Okay? So these statements that are assumed to be true, they don't require proof, are called axioms or postulates, either one of those terms. So to build a mathematical system, we've got undefined terms and defined terms. That's the vocabulary. We have to have the necessary terms to be able to communicate, right? In any system, not just mathematical system, we have to have the necessary terms. And note that when it says undefined, we're not being that loose with undefined, just throwing around random thoughts. No, I mean, we in the previous section, we talked about the point, the line, the plane. We defined those informally, but I mean, those are still some pretty rock solid descriptions that we gave about what a point is and what a line is, what a plane is. So, but it still wasn't a formal, official definition, which we'll talk about what makes a good definition in a second. Okay, so with a group of undefined terms that are still described very well as officially defined terms, you can build off of that vocabulary, and from that you get, so with these terms, there's certain characteristics of the system that become obvious or apparent, and you make these statements, these more like apparent, obvious statements that you don't have to prove, and those are called axioms or postulates. And then with the vocabulary combined with some postulates, some principles logically follow from this, and then you use deductive methods, kind of your formal arguments, and these more formal arguments that can be and need to be proved are called theorems. And so the axioms and the postulates and theorems, those are not vocabulary but principles. So what's the difference between vocabulary and principles? Vocabulary, we're making a statement. This is man-made vocabulary. Principles are these consequences of the vocabulary. They're not definitions. We informally defined a line. So one example that's always given of a postulate is between 2 points you can create a line. Okay, so we informally define a line. And I'm not going to go through the informal definition of a line, but you could come up with your own informal definition of a line. It's perfectly flat. However you want to informally define it. But the idea that between 2 points you can draw a line, well, we're not going to officially prove that. You don't have to officially prove that, but that's just kind of common sense. The line is some straight, again, we're not going to, you can go to law school to learn how to formally define a line, but and formally prove that 2 points contain a line, but we're not going to do that. There's going to be terms that we're going to build this mathematical system of geometry. We're going to be working with undefined terms and postulates, like the definition of a line. It's going to, again, we still we describe it. It's not like we're lazy with the description, but we just don't formally define the line. And then a postulate such as between 2 points you have a line. What does that mean? Can you prove that statement? Well, no. We're just going to assume that to be true. Okay, but so we start with undefined terms, and then maybe mixed in with that some postulates. But then from that we can come up with some defined terms that really require definition to build an official definition to build the system. Okay, so what are characteristics of a good definition? So terms such as point, line, and plane are classified as undefined because they do not fit into any set or category that has been previously determined. Yeah, exactly. So we're going to have to start with some undefined terms because what we're going to see is that, let's keep reading here. So terms that are defined, however, should be described precisely. But what is a good definition? A good definition is like a mathematical equation written using words. A good definition must possess 4 characteristics, which we illustrate with a term that we will redefine at a later time. So they're not giving the definition of definition here. We're going to look at the definition of isosceles triangle as an example. So this has 4 features that make it, 4 characteristics that make this a good definition. So an isosceles triangle is a triangle that has 2 congruent sides. There's the definition of isosceles triangle. Okay, so what are these 4 characteristics? In the definition, notice that 1, the term being defined, isosceles triangle, is named. Yeah, of course. You can't have a definition without including the term itself. 2, the term being defined is placed into a larger category, a type of triangle in this case. So yeah, with a good definition, you list the term, and then one feature of the definition is you're going to place it into a larger category. And that's where because you can go down a rabbit hole here where you say, well, okay, where does this all end? What if So this larger category, obviously the reader, whoever's the person, the student, whoever has to be familiar with this larger category, or else they're not going to understand the definition, right? So in this case, the isosceles triangle is a triangle. So we have to know what a triangle is. And so a triangle is going to have its own definition. Well, okay, if the word triangle has its own definition, well, to be a good definition, one of the features is it's placed in a larger category. Well, what's that category? And then what's the category of that definition? Where does this all end? Well, that's what they're talking about here. That's where these postulates and undefined terms, that's the role that they play. We're one of the reasons we're calling point, line, and plane undefined is because we can't really make a proper definition for them. And one of the reasons is that they don't fit into any general set or category. I mean, try and define what a line is. If you try and do that, notice though that your intuition is like, well, a line, it's obvious what a line is. I know what a line, it's hard to describe it, but any child that has a sense of what a line is. So it's obvious, but at the same time, it's kind of not though. You can't, it's kind of like this. That's when you get into what is truth, what is reality. No one knows what anything really is. It's kind of like that. You actually can't really define what a line is. Technically, we don't really. I mean, I guess we don't know. I mean, isn't space around us curved? So I mean, what is a line exactly? We don't really know. It's just our intuition. It's a like what a laser would do going in space. It travels along a line. I don't know how to describe it. But so since we can't define it, that means that we just say that we're ignorant. And well, no, we can all agree as a society that we can. This is common sense enough to where we can state these postulates and these informal definitions of these certain things to where we can then build off of that. It's sufficient to say, look, give some informal definition of what a line is perfectly straight. A line is, you have 2 points in space, and a line is going to travel through those 2 points. 2 points in space define a line. You can use all those informal descriptions to informally define a line. It's made up of postulates, right? The informal definitions are made up of postulates. Informal definitions of a point, a line, and a plane. A point in space. A point, right? That's a location in space. Oh, well, we don't know what space is. We don't. What is space? We can't define what a point in space is. No, we can use postulates to build a system. We can build a system by using postulates to define something like what a point is. It's a location in space that has no dimension. Okay? So, but we've got these foundational undefined terms, but from that we're actually going to need to build some official definitions to actually create the mathematical system. And so if you're going to actually define something, then you're going to be able to place it into a larger category. Like here, an isosceles triangle is what? It's a triangle. That's the second feature here. That you put the term that you're defining into a larger category that the reader is either familiar with, or they're going to go look up the definition of a triangle and become familiar with it. Okay. 3, the distinguishing quality that 2 sides of the triangle are congruent is included. So, yeah, well, it's not just a triangle, or else why would we be defining it? If it was just a triangle, well, that should then go to the definition of a triangle. It's within the category of triangles. So they've told us the category it's in, but what distinguishes it from everything else in that category? And that's like it has an adjective, right? I mean, not every definition has an adjective like this, but in this case, it's isosceles, which means it has 2 congruent sides. 2 congruent sides. So we need to know what congruent means, and to understand this definition, well, we looked at what congruent was in the previous section. Congruent is it's the parallel to equals. So you could have 2 numbers. Equals is stating that 2 numbers are the same. Congruent is stating that 2 shapes or figures are the same. in the sense that they can be oriented completely differently. But if you reorient one or both of them, you don't change the size, just reorient them. And you can, with that, you can flip them however you want in 3D space, line them up, and it's a perfect match. There's all the sides and everything perfectly matched. Then those figures are congruent. So we've got an isosceles triangle. They state the definition. It's a triangle where two of the sides are congruent. Means that we could take the two triangles, reorient them in space, and two of the sides, not necessarily the third, are going to line up perfectly. Then they're saying that that's an isosceles triangle. And also, when it comes to we can think about the sides of a triangle. And the fact the congruence means that their two sides are going to have equal length. It's another way of looking at congruence when it comes to line segments. And we know that the side lengths of triangles are line segments, or the sides of triangles are line segments. So, okay. Now, the fourth characteristic is reversibility of the definition. So what they're referring to here is you can state the definition from two separate perspectives. And this is the same idea as in the opening section, 1.1, the conditional statements, if this, then that. And you could flip it, and sometimes when you flipped it, it was true, and sometimes when you flipped it, it wasn't true. Same idea here. It needs to be reversible, a good definition. When you flip it, it's still true. So here, if a triangle is isosceles, then it has two congruent sides. Or if a triangle has two congruent sides, then it is an isosceles triangle. And so it is reversible. So that's a quality of a good definition. One of the examples we looked at with the conditional statement previously was, if you live in London, then you live in England. That's true. But if you flip that, if you live in England, then you live in London, that's not necessarily true. So that's not reversible. And so what they're saying is that any quality definition needs to be reversible. All right, so they review these characteristics of a good definition. You state the term being defined. You place the term into a larger set or category, which you'll be able to do if it's not one of the, if you're not at the end of the line where you can't do that, which means you're going to have work with some undefined terms or postulates. But other than that, you can place it into a larger set or category. Then it distinguishes the defined term from the other terms. And then also they state within that larger category, but they also state something else here without providing unnecessary facts. So keep it as concise as possible. And then it is reversible. Okay. Now they talk a little bit more about the idea of reversibility here. It says the reversibility of a definition is achieved by using the phrase if and only if. So yeah, if and only if, that's something you'll see a lot in math and science. So it's good to understand what they're talking about. And I'm going to go into this topic in a separate video in detail, because it can be confusing, because mixed in with if and only if is like necessary and sufficient conditions. And so we'll talk about all of that together in one video. But just to give you an overview here, anytime you see if and only if, you can think about that as that's just another way of writing the reversibility of a conditional statement. So in other words, if we come here, you can state that this definition here is reversible this way. Okay, kind of you write these two separate statements here, but you could also do it with if and only if, and write it as one statement. That's the idea. If and only if is just another way of showing the reversibility of something. That's it. Because you could say, they say if you wanted to define congruent angles, you could say two angles are congruent if and only if these angles have equal measures. And so you can see that the if and only if is implying the reversibility of, like, if you could just say without if and only if two angles are congruent, they have equal measures. Okay, you could say that. It's like saying, if you live in London, you live in England. That makes sense. But when you use if and only if, then you're fixing the reversibility of the statement, because it makes no, like, think about it. So two angles are congruent if and only if they have equal measures. If you're going to say if and only if, then this statement as it sits wouldn't make any sense if you couldn't say if two angles have equal measures, they're congruent. That makes no sense, right? So you see how the if and only if this statement wasn't reversible, then you couldn't, this sentence wouldn't make sense. So it's like you can condense down a double statement stating the reversibility of a conditional statement into one sentence using if and only if. And, this is a little confusing. If you're trying to apply this to the London example, this can be a little confusing. So, instead of spending too much time on it here, we're going to go through this in detail in a separate video. Because, again, the idea of a conditional statement, not a conditional statement, a necessary and sufficient condition is kind of mixed in here. So we're going to talk about this in a more detail in its own dedicated video. All right, when represented by a Venn diagram, the definition above would relate set C, the congruent angles, to set E, angles with equal measure, as shown in figure 1.30. The sets C and E are identical and are known as equivalent sets. So yeah, if you think about the two statements, C and E, about the equal measures and the congruence, for this to be reversible, they have to be equivalent sets that lie on top of one another. Well, if they're if they're equivalent, then they do lie on top of one another. If they didn't lie on top of one another, they'd be different sets. They'd contain different elements. So yeah, they lie on top of one another. It's not like one is a subset of another. They're equivalent sets. And that's the idea, because you can't have, if it's going to be reversible, you can't have certain situations where you have one without the other or the other without the one. You see what I mean by equivalent sets? These two are not equivalent sets. One is a subset of another. If this is C and this is E, one is a subset of another. These two, they're the same size, but they're not equivalent sets. You have different elements in set E than set C. So you can't, in this scenario or this scenario, you couldn't write a reversible statement, an if and only if, between set C and E, because there's situations where, you could live in England and not live in London, for example. C, you live in England, E, you live in London. Well, there is situations where you could, if you live in London, you live in England. That's true. But if you live in England, do you live in London? Not necessarily. So equivalent sets means they're the exact same set. They're the same size, and they lie on top of one another. Like here, which means you can write a reversible if and only if statement. So that's the idea of an equivalent set. Okay, once undefined terms have been described, they become the building blocks for other terminology. In this textbook, primary terms are defined within boxes, whereas related terms are often bold-faced and defined within statements. So it sounds like what they're saying here is that official definitions are going to be, in a box like this, but related, not officially, related undefined, not officially defined terms will just be bolded. I believe that's what they're saying. We'll see as we go. Maybe that's not exactly what they mean. We'll see. Okay, consider the following definition, and it's going to be based off this figure 1.31, segment AB. A line segment is the part of a line that consists of 2 points known as endpoints and all points between them. Okay, so if we think about this, here's the characteristics of a good definition. So they state line segment, and then they're going to put it into a larger category, and the category is a line, and that's one of the undefined, not officially defined categories. I don't want to say undefined, because we can describe line pretty well, and so we think of a line. We don't have an official definition for a line, but we have a good intuitive conception of what a line is. It's a part of a line. A line segment is a part of a line. Okay, it's a part of a line. So that's the bigger category that it's in. So, okay, but it's not a line. It's a kind of line. It's a subset of lines. So what distinguishes it? Here's all lines, and here's all line segments. So every single line segment is, well, it's a part of a line. I don't know if I guess I can say it like this, like a subcategory. It's a part of a line. So maybe this isn't exactly correct because a line segment isn't a line, but you get the idea. What distinguishes a line segment from, lines in general? Again, maybe this is not the best example. Well, okay, what distinguishes a line segment from a general line? So a line segment consists of 2 points, known as endpoints, and all points between them. So a line segment is it's a part of a line. So there we go. We have a line, and so I don't know if I'd call it a subset of a line, but it's a part of a line. It's a portion of a line that consists of 2 points known as endpoints and all points between them. So there's no there's no points that any point that's part of this line segment is going to be between the two, what they're calling the endpoints, not away from this. So like this is not part of this segment because it's not between the 2 points you picked. So it's the 2 endpoints and all the infinite number of points between them. So that's a good definition. It describes the larger category here. It's a part of a line. We understand what that means. And then it gives us a sufficient description of exactly what they mean by what a part of a line. Because maybe when it comes, we'll learn what array is. Array has an endpoint, but then it doesn't have another endpoint. So that's another way you could describe something that's part of a line. You could think about the sort of the subcategory of lines. Here's lines. You have rays and you have line segments. But there's no crossover here because there's no ray that's a line segment and there's no line segment that's a ray. Okay? And so now what about the reversibility? So let's see. Well, okay, the characteristics, we've got the term being defined. They present it. A line segment is defined as a part of a line. That's the category. The definition distinguishes the line segment as a specific part of a line, clearly, and the definition is reversible. So a line segment is the part of a line between and including 2 points. The part of a line between and including 2 points is a line segment. So you see how this might not, it's not like this is trivial when they're doing the reversibility here. You could maybe have a part of a line between and including 2 points is a line segment. What if there was a case where if there was a part of a line that was between and including 2 points, that it could be a line segment or it could be something else? And that would happen in the case of, so here's a part of a line between and including 2 points. That's A. Then you have line segments is B. And so line segments could be parts of a line between and including 2 points, but they can also be something else. Well, then that wouldn't be reversible. These need to be equivalent sets, A and B. Okay, we'll continue this section in the next video.